Mercury, the closest planet to the Sun, has long been known for its extreme temperatures and lack of atmosphere. However, in 2001, scientists uncovered a remarkable feature of this small, rocky world: a vast sodium tail stretching 2.5 million kilometers into space. This discovery challenged our understanding of planetary characteristics and prompted a deeper investigation into the planet's behavior and its interaction with the Sun. Astronomers had been studying Mercury's exosphere, its thin and tenuous atmosphere, using sodium filters since the 1980s. These filters were specifically designed to detect sodium atoms, a component found in small amounts in Mercury's exosphere. In 2001, a team from McDonald Observatory in Texas noticed something unexpected while observing Mercury with these filters. What they saw was not just sodium in the exosphere, but a faint elongated tail extending far behind the planet, far beyond what had been anticipated. This glowing sodium tail stretched across space, its size and scale unprecedented for a terrestrial planet. Measuring 2.5 million kilometers in length, about 700 times the diameter of Mercury itself, this discovery was groundbreaking. It suggested that Mercury was not just a small rocky planet, but a dynamic world with active interactions between its surface, atmosphere, and the solar wind. The origin of Mercury's sodium tail lies in a phenomenon known as sputtering. Mercury, due to its proximity to the Sun, is constantly bombarded by the solar wind, a stream of charged particles emitted by the Sun. When these particles strike the surface of Mercury, they transfer energy that can dislodge sodium atoms from the planet's surface. This process, similar to a powerful space erosion, releases sodium into Mercury's extremely thin exosphere. Mercury also faces bombardment from micrometeoroids, which contribute to the release of additional sodium atoms. The combination of solar wind and meteoroid impacts gradually erodes the planet's surface, sending sodium into the surrounding space. Once sodium atoms are released into Mercury's exosphere, they are pushed outward by solar radiation pressure. The Sun's photons interact with the sodium atoms, pushing them away from the Sun. This outward pressure creates a long, trailing sodium cloud behind Mercury, stretching across space like a comet's tail, but composed entirely of sodium atoms. While comets are known for their bright tails, which are composed of gas and dust particles, Mercury's sodium tail is different. Comets have tails made of material that sublimates from their icy cores, but Mercury, a rocky planet, does not have ice. Instead, the sodium tail is formed by the dislodging of sodium atoms from its surface, a result of solar wind interaction and micrometeoroid impacts. This makes Mercury's sodium tail a unique phenomenon in our solar system. The solar radiation pressure, though weak, plays a critical role in the formation and maintenance of Mercury's sodium tail. As solar photons hit the sodium atoms, they transfer momentum to the atoms, causing them to be pushed away from the Sun. This continuous pressure ensures that the sodium tail remains elongated, forming a permanent structure trailing behind the planet. Detecting Mercury's sodium tail requires specialized equipment. Sodium atoms emit light at a specific wavelength of 589 nanometers, which corresponds to the familiar yellow glow seen in streetlights. Astronomers use sodium D-line filters to isolate this specific wavelength and detect the faint glow emitted by the sodium atoms in Mercury's tail. Without this filter, the glow would be nearly impossible to detect due to the Sun's overwhelming brightness. Despite its enormous size, the sodium tail is not visible to the naked eye. It can only be observed through careful, precise measurements, often during the few windows in time when Mercury is positioned just right relative to Earth and the Sun. Mercury's sodium tail is not a static feature. It changes with the planet's position in its elliptical orbit around the Sun. When Mercury is closest to the Sun during its perihelion, the intensity of the solar wind increases, leading to an uptick in sodium release from the planet's surface. However, the tail reaches its maximum size 16 days after Mercury passes perihelion, as the planet's speed increases, optimizing the conditions for the tail to extend. This dynamic nature of Mercury's sodium tail highlights the planet's active interaction with the solar wind and its environment. As Mercury moves through its orbit, the tail fluctuates in size and intensity, offering new insights into the planet's behavior and its solar interactions. Observing Mercury's sodium tail is not an easy task. The planet's proximity to the Sun makes it difficult to detect the tail using Earth-based telescopes. Mercury must be positioned at a certain angle, far enough from the Sun to avoid the glare, and must be in the correct part of its orbit for the tail to be visible. These conditions make observations relatively rare, occurring only once every few years. The discovery of the sodium tail in 2001 was a stroke of luck. Astronomers had managed to observe the planet when the conditions were just right, allowing them to capture the faint glow and reveal the full extent of Mercury's sodium trail. Mercury's sodium tail offers important insights into planetary atmospheres and their interactions with solar radiation. While the loss of material from Mercury is gradual, over billions of years, it could significantly affect the planet's surface composition. The study of Mercury's tail also opens up new avenues for understanding the behavior of exoplanets. Many exoplanets orbit close to their stars, and it is likely that some of them experience similar processes, resulting in tails composed of various materials. Mercury's sodium tail also provides valuable data for understanding the behavior of small, rocky planets in general. It serves as a reminder that even the smallest bodies in the solar system can exhibit complex interactions with their environments, offering clues to their past and future evolution. With NASA's Bepi-Colombo mission scheduled to enter orbit around Mercury in December 2025, scientists will gain a more detailed understanding of the planet's sodium tail. This mission will allow for closer observations and more precise measurements, providing new insights into Mercury's surface, atmosphere, and the processes that create and shape its sodium tail. As we continue to explore the solar system and beyond, discoveries like Mercury's sodium tail remind us that even well-known planets can still hold surprising secrets, expanding our knowledge of the universe and the forces that shape it.